In sections 6.1 and 6.2 of this chapter, we had focused on finding confidence intervals for population means. In 6.3, we're going to switch gears. We're still going to be working with confidence intervals, but now we're going to try and find the confidence intervals for population proportions. Okay. A lot of the material that kind of goes with population proportions kind of mimics and follows that we saw back in 4.2 when we were doing binomial experiments. If you recall, a binomial experiment is one where we have we repeat a fixed trial a certain number of times. Each trial is supposed to be independent of the others, and each trial has only two outcomes, one of which we labeled a success, the other which we labeled a failure. We let n be the number of times the trial was repeated, p was our probability of success, q was the probability of failure, and in that context, x was our random variable that represented the number of successes in n trials. And we said that typically with that type of probability distribution, x always had a range from 0 up to a maximum possible of n. Okay. This time, we're going to be constructing confidence intervals for a population proportion or a percentage of the population. So the sample statistic this time, instead of being x bar, is going to be p hat. P hat is going to be the sample proportion, and that's going to be used as a point estimate for the actual true population proportion. For example, you could ask the question, what percentage of Americans have a favorable approval rating of the president? That true percentage could be something like 0.47 or maybe 0.53, but whatever the value would be for all people, that proportion, that would be the p-value. If I ask and sample 100 people, and 63 of them said that they approve of the president's job, then my sample proportion, my p-hat value, would be 63 over 100, which would be 0.63. Much in the same way that x bar, the sample mean, is a point estimate for the population parameter mu, which is the population mean, our p-hat, which is our sample proportion, is going to be a point estimate for the population proportion p. To construct our confidence intervals, again, it's going to begin with the point estimate. That's going to be the p-hat value. And we will again take that point estimate and subtract the margin of error and add the margin of error to it in order to create our confidence interval. In the same way that we do not usually know the mean of the population, oftentimes we do not know the value of the true population proportion p. But like mu, we can find a point estimate for p, and that's going to be p-hat. So how do we find our sample proportion? Well, we take our sample size, and we divide it into the number of successes we get. So if you're looking for, of course, the number of people that approve of the president, it would be the number that would say that they would, divided by how many people you sample, and that would give us our point estimate p-hat. We have the other estimate, which is going to be for q-hat, which would be those that do not have that proportion. And that's going to be found by doing 1 minus p-hat. For example, if 63% of the people would approve of the president, then 1 minus 0.63 of those other 37% or 0.37 would not approve. In the first couple examples, we just want to get some practice computing p-hat and q-hat. In example 1, they say that we have a survey, so this is our sample size, of 1,000 people. 520 of them believe that the role of unions in protecting workers' rights is as important today as what it was in years past. Find point estimates for P and Q. The point estimate for P is p-hat. That's going to be equal to x divided by n. Our sample size was 1,000. The number of people that did believe in the role of unions' rights was 520. So it's going to be 520 divided by 1,000, which is going to be 0.520. To find the value for q-hat, much like what we did back when we were doing binomial distributions, q-hat is always just 1 minus p-hat. So that's going to be 1 minus 0.520, which would give us 0.480. Let's do another one. In example 2, they say that we have a survey of 2,939 U.S. adults. 2,439 of them say that they have contributed to charity in the past 12 months. Let's construct the point estimate p hat and q hat. P hat's going to be the size of the sample, that's 2,939. And we're going to divide that by the x value, which is the number of people that say that they have contributed. That's the 2,439. And to 3 decimal places, that would give us a p hat value of 0.830. We can now go ahead and find the value for q hat. Q hat is going to be 1 minus p hat. That is 1 minus 0.830, which is equal to 0.170. So now that we know how to find p hat and q hat, we're ready to now start to construct our confidence intervals. To find the confidence interval for a population proportion, it's going to be p hat minus e to p hat plus e, where the margin of error is going to be computed using the following formula. E is equal to z critical, the critical z-score, times the square root of p hat q hat divided by n. In order for this to work, this assumes that the binomial distribution is normal for all of this to work, and a sufficient condition for that is that n times p hat and also n times q hat have to be greater than or equal to 5. In most practical applications, these conditions are almost always met, though you should always check them before you try to construct a a confidence interval of this form. Generally, the only time when this doesn't occur is, first of all, one, if you have a really small sample size n, you run the risk of one of these two inequalities failing, or if you're sampling in a population where either very little of the population has that quality or a lot of people have that quality, then that can also kind of throw off the inequalities here. But for the most part, these are usually met, and so we're able to kind of go ahead and compute these types of confidence intervals. Let's take a look at one together. They asked us to construct the 95% confidence interval for the population proportion and to interpret the results. In a survey of 420 U.S. females aged 18 to 64, 279 say that they have gone to the dentist in the past year. We want to construct the 95% confidence interval for the population proportion of all females of this age that have gone to the dentist in the past year. So to start, we want to begin by finding the point estimate for p hat and q hat. P hat is going to be the number of individuals that did say they went to the dentist. That's 279. That's our x value. Divide that by the size of the sample. That's 420. 279 divided by 420. That gives us 0.64. That's our point estimate for the population proportion. That's p hat. To find q hat, it's just going to be 1 minus p hat. So 1 minus 0.664. That's going to be 0.336. Before we do anything else, we should make sure that n times p hat and n times q hat are both greater than or equal to 5. If I take 420 and I multiply it by, that's my n value, and I multiply it by p hat, that'll certainly be bigger than 5. As 2, will 420 times 0.336 is going to be greater than or equal to 5. So we will be able to do our confidence interval here. So we're going to go ahead and find the z-score. The z-score we've done a bunch of times now. We want to find the z-score that corresponds to the 95% confidence interval. That would be simply a matter of going second distribution, inverse norm. The tail area, or the cumulative area, would be 1 minus 0.95 divided by 2. That's 0.025. It's a z-score, so mean of 0, standard deviation of 1. Go ahead and hit enter. And to 3 places, this would give us a critical z of positive 1.960. Once we have our ZC value, we can plug it into our margin of error formula. The margin of error for a population proportion is ZC times the square root of p hat q hat divided by n. That's going to be the 1.960 times the square root of 0.664 times 0.336 divided by 420. When you punch this into your calculator, it's very important that you input it in a way so that that whole fraction is under the square root. In the TI-83 or 84, you can do it as follows. I'm going to put 1.960. I'm now going to hit the square root button, which is the second x squared key. So if I hit second function x squared, that will pull up my square root. My TI-84 Silver Plus edition already comes with an input box that will naturally keep everything under that square root. If you have an older version of the 84 or even a TI-83, one of the things you can do to be safe is just put a parenthesis there and then start to enter this computation that's underneath. I can do 0.664 times 0.336 divided by 420 and right parenthesis, and that will keep that entire command under the square root to make sure I get the proper value here. If I take the margin of error and round it to 3 places, this is going to round to 0.045. So the margin of error is going to be 0.045. Once we have that, we're ready to go. Our confidence interval is p hat minus e to p hat plus e. This is going to be our p hat value from above. That was 0.664 minus 0.045 to 0.664 plus 0.045, which gives us a 95% confidence interval of 0.619 to 0.709. The interpretation of this is that we can say that we are 95% confident that the true proportion of U.S. females aged 18 to 64 that have gone to the dentist in the past year is between 0.619 and 0.709. So percentage-wise, we believe it to be about between 62 and 71%. This is how you would construct a confidence interval for proportion by hand. As we had back in the previous 2 sections where there was a z-interval command and a t-interval command, there is also a command to calculate confidence intervals for proportions, and it's called the one-prop z-interval command. It also has one of the easiest interfaces and inputs of any of our commands so far. This is under the stat, go to tests, and now you have to scroll down a little ways. Be very careful. There's some one prop z test things, but we're not doing testing yet. We're looking for intervals. If I continue to scroll down, I get to choice A here in the test menu. It says one prop z interval. That's computing a one proportion interval using z-scores, which is what we did. If I use this command, I can hit enter. And this command only needs 3 inputs. The first input is what is your x value? In other words, how many people had the desired quality? That was the 279. They want to know n, which was the sample size. That was 420. And then they also want to know what level of confidence are you using. For this problem, that is 0.95. If we go ahead and hit enter, it checks out with what we had gotten when we did it by hand. The confidence interval should be 0.619 to 0.709.